Welcome back to your second lecture this week for Physics 360. This is week 11, day 2, scheduled for release on April 3rd, and today we're going to be talking about Bessel's equation and Bessel functions. Just a reminder about some of the assignments that we have ongoing. Due today is paper homework 5 and the daily homework that was assigned on week 11, day 1. Due on Tuesday, the next time we, quote, meet, is the first draft of your project, as well as the daily homework that is being assigned today. And the only other remaining assignment we have ongoing is the next periodic homework 6, that is due on April 14th. So with all of that out of the way, let's talk about today's topic, Bessel's equation and the solutions to Bessel's equation, which are known as the Bessel functions. Bessel functions, you can think of them a little bit like damped sines and cosines. And Bessel functions pop up all over physics. Basically, any type of situation where you have cylindrical symmetry involved is likely to end up with some sort of Bessel function in there somewhere. This can apply in electricity problems, heat problems, fluid flow problems, elasticity problems, quantum mechanics problems, and many, many more branches of physics. And in order to explore what the Bessel functions look like and what their properties are, we are going to first derive their solutions from Bessel's equation, which is given as x squared times y double prime plus x times y prime plus quantity x squared minus p squared times y equals 0, where here p is some constant, not necessarily an integer, that is referred to as the order of the Bessel function. And before we try to solve this differential equation, it's useful to write these two terms on the left right here in a slightly different manner. Because these two terms, x squared y double prime plus x y prime, can be written in a different way. And that way is x times the quantity x y prime prime. So you take x, you multiply it by the derivative of y, you take the derivative of that quantity, and then you multiply it by x. And you can verify that you get what you need by running through the chain rule there real quick. But this means that, the product rule, not the chain rule. So this means we can rewrite our original Bessel's equation as x times quantity xy prime prime plus the x squared minus p squared times y term we have right here, all equals 0. And now we have ourselves a differential equation that we want to solve, and we are going to solve this by the method of Frobenius. So let me cordon off some room here, and we can begin. As before, the first thing we want to do is to write down an expression or a series for each of the terms in our differential equation. And we are going to do this by assuming a modified power series solution to begin with, which, as before, has the form of the sum from n equals 0 to infinity of a sub n times x to the n plus s. So this means, as before, we can write y prime as the following. The sum from n equals 0 to infinity of n plus s times a sub n times x to the n plus s minus 1. Then, the next thing to do is multiply this by x to find out what xy prime is. And all this amounts to is adding 1 to our power of x in our previous expression. So we get the sum from n equals 0 to infinity of n plus s, a sub n times x to the n plus s. Then we need to find our expression for xy prime primed. And we do that just by taking the derivative of this previous expression. And we get the following. The sum from n equals 0 to infinity of n plus s quantity squared times a sub n times x to the n plus s minus 1. And now we can finally get the last expression we really need here, which is x times xy prime quantity primed. And we basically take our previous expression that we had and we add 1 to the power of x. and we get the expression I just wrote. So now we're ready to make the method of Frobenius table that we've made before, where our lowest power of x is going to be x to the s. So let's make that table. So we have here columns for each of our powers of x, and we are going to have rows that match with each of the terms in our differential equation. So one of those is going to be our x times xy prime quantity primed. Another one of those is going to be just x squared y. And the last one of these is going to be negative p squared y. So let's fill out our table for each of these individually. This is probably something that you should try on your own to see if you get the correct answers, and then use this video to check your work. So for x times xy prime quantity primed, we're going to be working from this expression here. And to get our first term with x to the s, we need to plug in n equals 0. So we end up with just s squared times a naught is our coefficient. And then for the x to the s plus 1 term, we need n equals 1. So we end up with s plus 1 quantity squared times a sub 1. And so on and so forth. For the next one, we get s plus 2 quantity squared times a sub 2. And hopefully the pattern is kind of obvious by now. So the general term will just give us a coefficient of s plus n quantity squared times a sub n. For x squared y, note that the lowest power we're going to have of x is just going to be x to the s plus 2. And that will go with our a naught. So we're not actually going to have any terms for the first two columns for the x squared y term, and the n equals 0 term is going to give us a power of x to the s plus 2. So here, our coefficient is just a naught, and then our coefficient for our general term, where we have to plug in n equals n minus 2, is going to give us a sub n minus 2. Then for the negative p squared y row, this one's pretty straightforward. N equals 0 for the first one just gives us a coefficient of negative p squared times a naught, and that pattern will just repeat across the entire row, giving us negative p squared a1 for the next cell, and then negative p squared a2 for the next cell, and finally the general term where n just equals n gives us negative p squared times a sub n. Got a little ahead of myself back here. This cell should have been a sub 2, not a sub n. So now we can look at the column we have for the lowest power of x. And that is this column right here, the x to the s column, and set our coefficients equal to 0 to give us the indicial equation. And that indicial equation just tells us s squared a naught minus p squared a naught equals 0, or s squared minus p squared quantity times a naught equals 0. Now again, we've assumed that a naught is not 0, so this means the solutions to our equation are just going to be s is either plus or minus p. And it will turn out that when we take the s equals plus p version, we get something called Bessel functions of the first kind. And when we use s equals negative p, we get something called Bessel functions of the second kind. We'll also want to look at the general term here in order to get our relationship between the variables. So by looking at, let's pick a different color here. How about purple? By looking at this column here, we can get our general relationship as n plus s quantity squared minus p squared, that whole thing times a sub n, plus a sub n minus 2, all of that equals 0, which leads to the general relationship of a sub n equals negative a sub n minus 2 divided by n plus s quantity squared minus p squared. You've probably seen Bessel functions pop up here and there, but I at least want to give you an idea where you may have seen a Bessel function of the first kind, because I actually had a demo planned for today that we don't get to do anymore. It turns out if you hold a rope by one end and move the end you're holding in a small horizontal circle, you will establish kind of almost a standing wave in that rope. And the form of that standing wave is a Bessel function of the first kind. So now we are just ready to work through our solutions separately for s equals positive p and s equals negative p, the two values that we get from our indicial equation. So let's clear some room and work on this. So we're going to be starting with the s equals positive p solutions. First, we can look at the x to the s plus 1 column and see that we get that a1 has to be equal to 0. Then we can look at the general term to see how the rest of our terms and their coefficients relate to each other. So our general term simplifies after we plug in positive p for s to a sub n equals negative a sub n minus 2 over n times quantity n plus 2p. This means we're only going to have even values of n, so we may as well save ourselves a little notational difficulty later and just replace all of our n's with 2 n's to represent only even numbers. Which gives us the following expression for a sub 2n. Which can be rewritten in a way that might seem a little weird, but it's going to make the pattern more obvious later. Can be written as negative a sub n minus 2 divided by 2 squared times n plus p, that quantity in parentheses. So before we go any further, I want to remind you all what a gamma function is, because gamma functions are going to come into this solution process here. A gamma function is a lot like a continuous factorial function. So if you take the gamma function of p plus 1, this is equal to the quantity p plus 1 times the gamma function of just p, which is similar to the idea that p plus 1 factorial is equal to the quantity p plus 1 times p factorial. And indeed, the gamma function, when p is an integer, is related to the factorial in the following way. The gamma function of p equals p minus 1 quantity factorial. So this notation is going to help us simplify what we're about to write down about our Bessel functions of the first kind. So using this notation, we can then say that a sub 2 is equal to negative a sub 0 divided by 2 squared times 1 plus p. Which, this might seem weird, and it is weird, but this will help us later. We can then rewrite as negative a naught times the gamma function of 1 plus p divided by 2 squared times the gamma function of 2 plus p. If you look at how the gamma functions break down into factorials, you should be able to convince yourself that these two expressions are equivalent to each other. So let's move on to the next one now. A sub 4 will equal negative a sub 2 divided by 2 cubed this time times 2 plus p, which we can then plug in our expression for a naught, or for a2 in terms of a naught. We get that a4 is equal to a naught over 2 factorial times 2 to the 4th power times 1 plus p times 2 plus p, which we can then write using gamma functions again as a naught times the gamma function of 1 plus p divided by 2 factorial, 2 to the 4th, times the gamma function of 3 plus p. So again, use what we know about gamma functions and try to convince yourself that these two expressions are equivalent. You'll want to get familiar with the idea of using gamma functions as part of your Bessel functions. Let's do one more of these just to double check. A6 is going to be equal to negative A4 divided by 3 factorial times 2 times 3 plus p. You might be asking yourself where the other 2 went. Well, we've kind of combined the n we get for n equals 3 and one of the 2's from the 2 squared in order to make that 3 factorial. Then we plug in our expression for A4 in terms of A0. And we end up with negative A0 divided by this whole big thing. 3 factorial times 2 to the 6th times 1 plus p times 2 plus p times 3 plus p. And see if you can figure out how we're going to write this in terms of gamma functions before I write down the answer here. Because we get the following for A6. Negative A0 divided by 3 factorial times 2 to the 6th. And then on the numerator, we have a gamma function of 1 plus p. And in the denominator, we have a gamma function of 4 plus p. So I'm kind of hoping that the pattern is starting to become a little evident now, and that we can start to write out the overall form of this series. So just working down here, we can now start to write our expressions for y using this gamma function notation. And what we find is that you end up with y is equal to factoring out an a0 times x to the p times the gamma function of 1 minus p. The rest of our terms then become the following. The first term is 1 over the gamma function of 1 plus p. Then the next term involves minus 1 over the gamma function of 2 plus p, with this function having an x over 2 quantity squared. Then the next term is positive and has a 1 over 2 factorial times the gamma function of 3 plus p. And again, there's an x over 2 term, and this time it's to the 4th power, minus 1 over 3 factorial times the gamma function of 4 plus p times x over 2 to the 6th power, and so on and so on. We haven't written the factorials in for every term, but note that you could very easily put a 1 factorial here, because 1 factorial is equal to 1, and you could very easily put a 0 factorial here, because 0 factorial is also equal to 1. So you can rearrange this a little bit to make the pattern more obvious, and I'm actually going to replace what I have in the denominator for these first couple terms in order to make the pattern that we're dealing with here more obvious. So the first term, or all of these terms, that first term just becomes gamma of 1, there's your 0 factorial, times gamma of 1 plus p. The second term has a gamma of 2, again equal to 1. Gamma of 2 is 1 factorial, times the gamma of 2 plus p. Well, now in our next term over here, we have this 2 factorial, and we can write the 2 factorial as the gamma of 3. And the 3 factorial in the next term, we can write as gamma of 4. So we have a nice repeating pattern in terms of our gammas. And this is almost to the point where we are ready to call this a Bessel function of the first kind. All we need to do now is pick a specific value for a0. And the value we're going to use is a0 is equal to 1 over 2 to the p times the gamma function of 1 plus p, which could be written in factorial form as 2 to the p times p factorial. When a0 has this specific value, our function y above is called a Bessel function of the first kind. So we can now write out the more general form of our solution here. And writing it out term by term, we get the following. Jp of x is equal to, with the appropriate value of a naught, your first term is 1 over gamma of 1 times gamma of 1 plus p, all times x over 2 to the p power. Remember, because our first term is x to the s, and s is equal to p for this case. Then our next term is going to be 1 over gamma of 2 times gamma of 2 plus p. This term is times another factor of x over 2, this time taken to the p plus 2 power. Then hopefully you're picking up on the pattern now. The next term is going to be 1 over gamma of 3 times gamma of 3 plus p, this time times x over 2 to the p plus 4 power, and so on and so on. So if we want to write this in a single form with summation notation, we have the following. Jp of x, the Bessel function of the first kind, is equal to the sum from n equals 0 to infinity of negative 1 to the nth power over gamma of n plus 1 times gamma of n plus 1 plus p, that whole thing times x over 2 quantity to the 2n plus p power. And this is our Bessel function of the first kind. Now we want to do the same thing to try to find Bessel functions of the second kind. When s equals negative p, the solution we get will be called a Bessel function of the second kind. We're not going to go through the entire process again because it really just amounts of changing a p to a minus p. So at the end of the day, we get the following expression for our Bessel function. Well, it's not a Bessel function of the second kind yet, but for our solution, we get j sub negative p of x is equal to the same sum from n equals 0 to infinity that we had before, times the same negative 1 to the n in the numerator, and in our denominator, our first gamma function is still n plus 1, but our second gamma function is n plus 1 minus p rather than n plus 1 plus p. And we still have our x over 2 to some power, but now that power is 2n minus p rather than 2n plus p. It's important to note that the relationship between j of p and j of minus p, or j sub p and j sub minus p, is actually pretty straightforward when p is an integer. J sub minus p of x equals negative 1 to the p power times j sub positive p of x. So this means when p is an even number, j sub p equals j sub negative p. And when p is an odd number, j sub p equals negative j sub negative p. This also has some relevance in terms of our solution to our differential equation. This means that when p is an integer, this new solution, j sub minus p, is not an independent solution of our differential equation. So really, Bessel functions of the second kind are only really useful when you're using p that is not an integer. When p is an integer, the Bessel functions are effectively just slight modifications of our original Bessel functions of the first kind. So now for something a little bit weird that falls under the category of tradition and just how we do things. Rather than using this equation that we just found as our Bessel functions of the second kind, we give them slightly different names, and we write them as a linear combination of j sub p and j sub minus p. So when p is not an integer, we're going to use the linear combination of our two solutions to represent our Bessel function of the second kind. And recall that this is allowed. If you have any two solutions to a differential equation any linear combination of those two solutions is also a solution to the differential equation. So at the end of the day, what we get is our Bessel function of the second kind can be given either by n sub p or sometimes as y sub p, both as a function of x, and it is given as the following linear combination in jp and j minus p. In the numerator, we have cosine of pi p times j sub p of x minus j sub negative p of x all over sine of pi p in the denominator. And this is our Bessel function of the second kind. There's a couple things I want you to note about this equation. One of them is that it seems like this equation would be very simple when you plug in p as an integer, because the cosine of some integer times pi and the sine of some integer times pi, well, the sine of any integer times pi is just 0. And the cosine of some integer times pi is negative 1 times the multiple of pi. So in the situations when p is an integer, we get the following. And before we freak out, because this is divided by 0, we should look at our numerator again. And we should look at our numerator in the context of this relationship between jp and j minus p when p is an integer. And that tells us that our numerator is also going to be equal to 0. So when p is an integer, we get 0 out of 0 for the Bessel function of the second kind, which is kind of part of why we don't really use it for integers. But even though this has a value of 0 over 0, this expression does have at least a well-defined limit as p approaches an integer. Think of a function with a hole in it, but where if you approach that hole from the left side or you approach that hole from the right side, you get the same value of y as your limit there. And because of this well-defined limit as p approaches any integer, even though you get 0 out of 0 if you plug in the integer value directly, this means that Bessel functions of the second kind can be used for any value of p. I want to take a little minute to look at the graphs of Bessel functions, both of the first kind and of the second kind. So you can see these here with the Bessel functions of the first kind on the left and the Bessel functions of the second kind on the right. And you can see that all of these look an awful lot like damped sines and cosines, as I mentioned before. But another thing I want you to notice is that the zeros of this function are not evenly spaced, like damped sines and cosines would be. So with a damped sine or a cosine, which has the following form, we would still expect our zeros to be evenly spaced. With our damped sine and cosine having a 0 every pi, we travel along the t-axis, or whatever axis we're using as our independent variable. But let's look at how this applies to our Bessel functions. So we can look at a couple of these, and we can look at j sub 0, which has its first 0 right here, then its second 0, then its third 0, and so on. We can look at j sub 1 in orange, which has zeros here. We can look at j sub 1, which has zeros here. We can look at j sub 3, which has its zeros here. We can look at j sub 4, which has its zeros here. Well, it might not be easy to see that these zeros aren't evenly spaced just by this graph right here, but I want to draw your attention to some of these zeros specifically. So for j sub 1 in orange here, we actually have 1, 0 when x equals 0. So that means there's this much space between the first two zeros. And then when we get further along, we have less space between the zeros. So it's a little difficult to see, but hopefully you can convince yourself that for this first zero, the first two zeros, there's just a tiny bit under 4 of a difference between them. But way down here at the end, our first zero seems to be at about 16.5, and our last zero seems to be at around 19.5, spaced by only about 3. It'll turn out this is actually pretty close to pi. Another way we could look at this is to look at some of our zeros of our blue and green functions. So our blue function has a 0 here, and our green function has a 0 here, and these are spaced by some amount. But if we go a little bit further on, actually let me pick different ones for that. Green has a 0 here, and blue has a 0 here, and these are spaced by about that much distance on the graph. But if we go all the way to the end of the graph, to this point right here, well, then we have our zeros spaced by a much smaller amount. So the spacing between the zeros of both of these functions is not uniform. But even though the spacing between them is not uniform, it does at least have a well-defined limit. As x goes to infinity, the spacing of the zeros approaches pi. Just one quick little reminder, if you are recalling the relationship from the previous page, that j sub p of x is -1 to the p times j sub negative p of x. And then you're looking at all of these Bessel functions of the second kind and wondering why these don't just look like the Bessel functions of the first kind multiplied by a 1 or -1. Note that these are not our j sub minus p of x expressions right here. These are instead our y sub p or n sub p expressions. So this is already the linear combination of our j sub p and our j sub minus p functions that we found on the previous slide. This lecture is a little on the short side, mostly just because I was going to make you all do this as an in-class activity. But I really do recommend making sure that you could work through that method of Frobenius solution to the Bessel function, to the Bessel equation yourself, and that you understand fundamentally what the Bessel functions look like and what their formulas are, and the difference between Bessel functions of the first kind and Bessel functions of the second kind. That's all I have for you today. Thank you for watching, and have a good weekend.